Okay, so now that we've gone over the Henderson-Hasselbalch equation, we're going to go over how to select the most appropriate weak acid and conjugate base for making a buffer at a specific pH. Let's say you wanted to make a buffer at pH 7, or at pH 9, or at pH 2. What weak acid and conjugate base would you use to make a buffer at those pHs? Well, a buffer has its most buffering capacity when concentration of weak acid is about the same as the concentration of weak base in the buffer. You want to make a buffer where the concentration of weak acid and weak base are both significant and about the same. You don't want to make a buffer where the concentration of weak acid is a lot more than the weak base or vice versa. Because if, for example, the concentration of weak acid is a lot more than the weak base, you have very little weak base in there. And so then as soon as you add a little bit of hydrogen on, you run out of your weak base and then the buffering capacity is gone, so you no longer have a buffer, or vice versa. So that's why you want these concentrations to be the same. So if you look at the Henderson-Hasselbalch equation, which gives you a better insight as to how buffers work, when these two concentrations, weak base and weak acid in a buffer, are about the same, this ratio is 1, log of 1 is 0, so this drops out. So that's when pH is equal to pKa. So the best weak acid to choose to make a buffer at a certain pH should be the one in which its pKa is equal to the pH of the buffer. Because in doing so, then the concentration of the weak base and weak acid in the buffer have to come out to be about the same. So therefore, the most appropriate weak acid is the one that has its pKa closest to pH of the buffer, or its Ka closest to hydrogen ion concentration in the buffer. So let's do an example now. Again, you can close your eyes so you don't get dizzy. Again, still keep your eyes closed so you don't get motion sickness. Okay, I think I got it. Let me just zoom in a little more. Okay. Okay, you can open your eyes now. So, in this question, it says, given the following weak acids, so you have these weak acids, you have their Kas. Again, all of that will be given to you in the table during the exam, as well as it's in sample exam 1. So you are given the Ka values. Phosphoric acid has Ka2 and Ka3. We've already covered this, but as a reminder, Ka2 of phosphoric acid is actually Ka of dihydrogen phosphate. And Ka3 of phosphoric acid is Ka of monohydrogen phosphate. And we, again, write it this way because it takes less space rather than put dihydrogen phosphate here and write a Ka for it. So anyways, it says identify the best weak acid and sodium salt, conjugate base, for making a buffer at pH 4.74 and pH 7.3. Now, if you have a lot of weak acids to choose from, then the easiest method is to compare, rather than take the negative log of all these values and get the pKa, convert the pH into hydrogen ion concentration and see which one of these has its Ka closest to the hydrogen ion concentration. So the hydrogen ion concentration is equal to 10 to the power of minus pH. So 10 to the power of minus 4.7. And so when I do that, let's see, 4.7 inverse log. It's 2 times 10 to the power minus 5. So when I look, the closest Ka to that is Ka of acetic acid. So therefore, acetic acid and its sodium salt, sodium acetate, must be used to make this buffer. So I'm going to use a solution of acetic acid and sodium acetate, mix them together to make this buffer. For the next one, if I were to calculate the hydrogen ion concentration, 10 to the power minus pH, 10 to the power minus 7.3. So So inverse log 5.0 minus 8. So again, the closest to that would be this one, 6.2 minus 8. So that's dihydrogen phosphate. Dihydrogen phosphate is an anion, it doesn't come by itself. So I would use sodium dihydrogen phosphate and sodium monohydrogen phosphate to make this buffer. And so by doing that, when I calculate the amounts, I'll see that these concentrations will be close to each other. I won't have one of them be 1 molar, the other one like 10 to the power minus 3 molar. Now, how do you figure that out? How do you calculate those concentrations? That's what we're going to do in the next video.